I saw I made my last video 1 year ago, so it was high time for an update. In that video I showed capacitor thrust measurements using a microgram scale with mixed results, followed by an attempt at a 500 volt solid state pulsed pendulum setup, which did not yield any movement visible with the naked eye. I then later tried the same experiment using a higher voltage and a spark gap, which did set the pendulum visibly in motion, which was incredibly exciting. And even more exciting was that it moved in the direction predicted by the theory of quantized inertia towards the anode. I then further verified this by changing the polarity of the capacitor, which then also changed the direction of the thrust. So yeah, this got me pumped. But something similar was also already shown in a video by Master Evo, who mentioned to me that the next obvious step would be to perform the experiment inside a vacuum chamber to exclude ionic wind as a potential explanation for the observed thrust. And oh boy, did I underestimate this. Because I ordered myself a tiny vacuum chamber. It's like 20 cubic centimeters. And I drilled a hole in its side, built my own high voltage vacuum feed through. It was a lot of work, but it all worked out all right. Apart from the fact that my first vacuum pump that I received started smoking as soon as I turned it on. It's a little setback, but it's all right. The main issue I encountered was described beautifully in this NASA article, actually. It says, for a 1 centimeter gap of air, breakdown at the atmospheric pressure of 760 torr would occur at about 30 kilovolts, whereas at the pressure of 0.6 torr, it would require only about 300 volts DC. In other words, in a vacuum, a spark needs 100 times less voltage to jump the same distance. And this was causing arcs everywhere. And I tried all kinds of things to prevent this, but in the end, the only thing that really worked was distance. So I finally calculated that at 5 kilovolts, I needed about 20 centimeters of dielectric distance to contain the arcs, which made me come up with an elaborate Kapton foil wrap per capacitor plate, as well as using Kapton wires. This did indeed work and contained the arcs. The downside, however, of the extra Kapton foil was that it made the capacitor way heavier. And the downside of the Kapton wires was that they are very stiff, both making it much harder for the pendulum to be able to swing freely. And yeah, we're working with very low thrust levels, so it's very hard to set it in motion. And this was on top of the fact that my tiny 20 cubic centimeter vacuum chamber only allowed the pendulum arm to be rather short, further complicating its free movement. So at this point I started running out of ideas, so I decided to ask Grok AI to help me brainstorm ideas. And in order to do that, I turned all my handwritten notes, video transcriptions, Patreon posts, QI articles and more into markdown files, combined them all into one workspace, and let Grok give me a daily tip on what to try next. The first suggestion it gave me was to try using a laser to create an optical lever to make minuscule movements more pronounced. But the laser got scattered by the acrylic walls of the vacuum chamber, making it impossible to use. It then suggested I try using 240 frames per second slow motion video in combination with the tracker video analysis software for physics. But I either wasn't able to see any movement or there was user error involved, so still no cigar. I was about to give up until I was chatting with Grok about how they measure thrust for pulsed plasma thrusters and other micro thrusters. And it told me they often use something called a torsion balance. This was originally used by Coulomb to measure electrostatic attraction and repulsion forces, but can be adapted to measure tiny amounts of thrust. So my new plan is as follows. Create a PCB that can attach to the back of the capacitor, which can charge the capacitor to 5 kilovolts using a Bluetooth trigger, so no torque is applied by lead wires and no high voltage vacuum feed-through is necessary, and then discharge the capacitor automatically through a gas discharge tube on the PCB. So step 2 is to build a torsion balance and test it out in the open air. If this works, I will get a larger vacuum chamber and test the torsion balance inside the vacuum chamber. So I've only just started down this road, but it was high time for a progress report, hence this video. Unfortunately, I'm not a master PCB builder and AI is terrible at it as well, but AI is great at writing code. So this is why I was thrilled to find the Skiddle project on GitHub, which allows you to define a circuit using Python code and which outputs a KiCad compatible netlist. So I've now built an elaborate Claude Code plugin which helps me write the Skiddle Python code, and within 1 hour it helped me design a circuit that starts with 2 coin cell batteries powering a Bluetooth module that listens for the trigger signal, then a 30-volt boost stage followed by a Cockcroft-Walton voltage multiplier that pushes the voltage to over 4 kilovolts to charge the thrust capacitor with, and finally a gas discharge tube to rapidly discharge the capacitor once it reaches the threshold voltage. I currently have the working netlist and I'm now in the process of manually trying to lay out the components on the board, which is quite tricky actually due to the limited space and the high voltage creepage requirements, and I'm sure I will fry a few of these boards before I get it working. So wish me luck, and please let me know in the comments if you have any suggestions for this next phase of experimenting. If you think I'm going down a dead end with this idea, or if you see improvements I can make, I'm very happy to hear your ideas. And I hope that my next video will be out in less than 1 year this time. So see you next time. Bye bye.